Welcome to this live session for week 6 contents, lecture contents of this course on hydraulic engineering. So this particular session is dedicated to the flow in open channels. So I hope that you have already gone through the lectures. So we'll directly start with the example problems. So the first problem is this one. So there is a trapezoidal channel which has a bed width of 2 meter and it has a side slope of 1.5 horizontal is to 1 vertical. The channel has a longitudinal slope of 1 by 4000, that is the bed slope, and the Manning's roughness coefficient of the channel boundary, that is the side wall as well as the bed, is 0.018. Now we need to calculate the mean velocity, that is the uniform velocity, and the discharge in the channel when the flow depth is 1.4 meter, that is the normal depth denoted by yn. Okay, so this is the problem. So for solving this type of problem, it is always advisable to first draw the problem figure. So this is the problem figure. So this b is the bed width, the width of the channel bed, the value of which is 2 meter, and this is the side slope. So side slope is 1.5 horizontal is to 1 vertical. So with respect to this figure, it is 1 vertical is to m horizontal. So the value of m is 1.5, value of v is 2 meter, and the flow depth y is 1.4 meter. Okay, so for this we need to find the discharge and the velocity. So since Manning's roughness coefficient is given to us whose value is 0.018, we need to use Manning's equation. So what is Manning's equation? V is equal to 1 by n r to the power of 2 by 3 s to the power of half. And what is this r here? This r is the ratio of weighted area by weighted perimeter. So first of all, for this trapezoidal section, based on its geometry, we need to determine the weighted area and the weighted perimeter. So let us look at the solution. So the area for this channel, if you do the calculations, will be a equal to b plus my into y. Okay, so how we have obtained this result? If you draw a line here, a vertical line, this is 1 is to m, then just by using the trigonometric ratio, say this angle is theta. Okay, so for this, if this angle is theta, then this angle will be theta. So if you just equate the trigonometric ratio, maybe sine theta or maybe tan theta, okay, you will get the values of y in terms of m. Okay, and you'll get the value of the top width t in terms of m as well. So based on these calculations, which I am leaving as an exercise for you to do, because this is a very simple calculation, but I will suggest you for competitive exams you should remember these values. Okay, these expressions. So area is a plus b, a equal to b plus my into y. The value of b is 2 meter. The value of m, that is the horizontal slope of the side slope, is 1.5 into y, that is the flow depth is 1.4 into 1.4. So it came out to be 5.74 meter per square. Sorry, meter square. Then what is weighted perimeter? So weighted perimeter is the length this plus this plus this. Okay, so it is b plus twice of y square root of m square plus 1. So basically the length of one slanted slide, okay, the length of one slanted slide is twice m square plus is y into square root of m square plus 1. But since there are two slanting lengths, so it is twice of this. So b is 2 plus 2 into square root of the value of m is 1.5, value of y is 1.4. So the weighted perimeter came out to be 7.048 meter. So I'm giving you 5 minutes so that all of you can arrive at these two expressions, the expression for a and expression for p, for this given trapezoidal section. This is a very simple calculation. Okay. So is there any doubt? Okay, if there is no doubt, I think all of you have arrived at the same expression. So let us move to the next step. So next is the calculation of the hydraulic radius R, which is the ratio of the wetted area by wetted perimeter. So 5.74 divided by 7.048, which is 0.814 meter. Okay, now if we use Manning's formula, V equal to 1 by N, R to the power 2 by 3, S to the power of 1 half will be there, S to the power of half. Yeah, so it will be 1 by 0.018, 0.814 to the power of 2 by 3, 1 by 4000, that is the bed slope, raised to the power of half. So the velocity is 0.766 meter per second, and the discharge Q is A into V, where A is 5.74 meter square and the velocity is 0.766 meter per second. So the value of discharge is 4.4 meter cube per second. Okay. So this is a very simple problem which illustrates the application of Manning's equation. Now there may be a variant to this problem where Chase's roughness coefficient will be given to you, and from that you need to apply Chase's equation to get the value of uniform velocity and the discharge. Okay. One more variation may be that Chase's equation is there, and from there you need to compute the value of Manning's equation, so Manning's roughness coefficient, and then you need to make use of Manning's equation or otherwise. Okay, so it is very important to know the mathematical relationship between Chase's constant and Manning's constant. Okay, so these particular points are very important for your competitive exams. Then you should also know the dimensions of the Manning's coefficient and Chase's coefficient. Now next problem, so it is little bit complicated with respect to the first problem that we have solved. So you have to show that the vertical distribution of velocity is parabolic for uniform laminar flow in a wide open channel. Now what is a wide open channel? A wide open channel is one where the bed width B is much greater than the flow depth Y. Okay. So you have to show that the vertical velocity distribution is parabolic. Okay, it follows a parabolic distribution. The vertical velocity follows a parabolic distribution for uniform laminar flow in wide open channel whose bed slope is constant and depth of flow is also constant. So if the depth of flow is constant, that itself is coming from the word uniform. Okay, and there is a constant slope. So let us look at the problem figure. This is the problem figure. So this particular line represents the longitudinal slope, okay, the bed slope or the channel bed. This is the free surface. Okay, now this is the velocity distribution and you have to show that this distribution is parabolic. Okay, so your task is to prove that, or you have to show that this velocity distribution is parabolic in nature. So how to do this? Let's see. Let the depth of the flow be h. So this is the depth of the flow which is perpendicular to the channel bed. So let the depth of the flow is h. Okay, you have to select a control volume whose length is dl and the control volume is marked by a b c d a. So which one is the control volume? It is this a b c d a. So this is the control volume whose length, so this length is dl. Okay, and the width of this control volume is b. So what is the width? Width is the direction perpendicular to the plane of this screen. Okay, so if you go to a direction which is so see, this is your x direction, this is your y direction as per the problem figure, and this is your z direction. So the width is the dimension of this control volume along the z direction. So the width is b. Okay, now we have to make use of the principle of conservation of linear momentum. Now if we have to apply the principle of conservation of linear momentum to this control volume, then what are the surfaces? Surfaces AB and surfaces CD. So what are the forces that are acting? The forces are the pressure forces, that is the hydrostatic pressure forces, say force F1 and F2 acting on face AB and CD. Okay, So force F1 is acting on face AB and force F2 is acting on face CD. Okay. Now, apart from that, what is the other force? Other force, see, if this is the flow direction, if this is the flow direction, this is the flow direction, then there will be shear stress which will be acting, or there will be shear force which will be acting opposite to the direction of flow. So this is represented by, the shear stress is represented by tau. And then for this control volume, what is the body force? That is the gravitational force, that is the weight. Okay. Now, if you apply the law of conservation of linear momentum, which is coming from Newton's second law of motion, then what is Fx? That is the force acting along x direction. It is F1. If you consider this, that the positive x-axis is the direction of positive forces, okay, then it will be F1 minus F2. Okay, F1 minus F2. Then tau, that is the shear stress. Okay, so this is shear stress. So if you want to get the shear force, then you have to multiply this with some area dA. What will be that area? Tau. dA will be, see, it is acting on how much, which area? So it is the width B into length dl. Okay, so tau dl into B. Okay, negative in the opposite direction. And what else is there? Rho g hy dl b sine alpha. What is this? This is nothing but the component of the weight of this control volume along the flow direction. Okay, the component of the weight along the flow direction. And what is this angle alpha? Okay, see, the angle alpha is this one. The channel bed is making an angle alpha with the horizontal. Okay, so this is angle alpha. So see, rho into h minus y. H minus y is what? This is the total depth h. Okay, y is what? Y is the depth of y is the distance of the lower surface. The perpendicular distance of the lower surface of this control volume from the channel bed is y. So what is the effective length? Means this particular dimension for this control volume, it will be h minus y. So from a to b, okay, ab equal to cd is equal to h minus y. Okay, so what will be the volume? Volume will be h minus y into dl into b. Okay, so h minus y into dl into b. Okay, so this represents the volume. Now if you multiply it with density, you will be getting mass, and mass into acceleration due to gravity is the weight. But we want the component of the weight along this direction, so you have to take the sine component, so sine alpha. Okay, and it is, this is also acting along the positive x-axis, so it is having a positive sign. Okay, but based on this diagram, okay, this F1 and F2 are same and acting in the opposite direction. Okay, so F1 and F2 are equal, so the net force Fx is, so F1 minus F2 will be 0, so rho g h minus y dl b sine alpha minus tau dl beta. Now for a steady uniform flow, the momentum coming into the control volume across the face AB is equal to that leaving from the control volume across the face CD. So this you can easily arrive at if you have followed the lecture and the applications of Reynolds transport theorem. If it is steady uniform flow, then the time component part will be 0, and uniform means the variation in the flow parameters with respect to different locations on the channel bed is 0. So the momentum that is coming into the control volume across the face AB is equal to the momentum that is leaving the control volume through face CD. Therefore, the net rate of momentum flux from the control volume is 0. Okay, so hence we can write that this Fx will be equal to 0. Means initial and final momentum are same, so it is 0. So from this equation, what will be the value of tau? Rho g h minus y sine alpha. For laminar flow, tau is equal to mu du by dy, that is Newton's law of viscosity. Now du will be what? Du rho g mu h minus y sine alpha dy. Okay, so this is du. So du by dy, see, tau is this expression. Okay, tau is this particular expression. So if you replace tau with this expression in this equation, then du can be written as rho g h minus y by mu sine alpha dy. And if you integrate, you will be getting rho g sine alpha by mu hy minus y square by 2 plus c1. So here itself you can see the variation of u with y is basically y is having a power of 2. The highest degree of y is 2. Okay, so this is parabolic variation. But what will be the exact variation? For that we need to determine the value of this constant c1. For small values of alpha, see, normally in natural open channels the value of alpha is very small, and for small values of alpha, sin alpha is equal to tan alpha is equal to the slope of the channel bed. The constant of integration is c1. So what boundary condition we can apply? At y equal to 0, the value of e equal to 0, because of no slip condition. Okay, because of no slip condition, the value of u at y equal to 0 is 0. So if that is the case, then if you put u is equal to 0 at y equal to 0, then this entire expression becomes 0, and as a result c1 becomes 0, and hence the value of u is this, which shows or which proves the parabolic distribution. So is the problem clear? Any doubt? Okay, so if there are no questions, I assume that there is no doubt and everything is clear. But this is a very important problem. It's a sort of unconventional problem. So please uh, go through this problem once. Okay, so let us move to the next problem. A rectangular channel 9.14 meter wide carries 7.64 meters cube per second of discharge when flowing 914 mm deep. So the width of the channel is 9.14 meter. The discharge is 7.64 meter cube per second. It is a rectangular channel and the depth of flow is 914 millimeter. You have to determine the specific energy and you have to determine whether the flow is tranquil or rapid. Okay. So specific energy is ES plus, so what exactly specific energy? It is H, that is flow depth, plus V square by twice G. Okay. For a rectangular channel, this can be written as H plus V square can be written as Q square by 2G A square. But for a rectangular channel, what is A? A is equal to B into H. So H plus Q square divided by 2G B square by B square into H square. Now Q by B can be written as small q, which is the discharge per unit width. So H plus Q square divided by 2G H square. Okay. So Q square 2G H square. So this is the expression for specific energy. Now this value of H, that is the flow depth, is 914 millimeter or 0.914 meter. The value of Q is 7.64 meter cube per second. Okay. Now this is capital Q. So what will be small q? Small q is capital Q divided by small b. So capital Q is 7.64, small b is 9.14. So 7.64 by 9.14 whole square, that is Q square. 2 into 9.81 is 2G. A square is 0.914 square. So the specific energy is 0.957 meter. Okay, this is the specific energy. Now, once you have determined the specific energy, next you need to determine what is the critical depth YC. So, the critical depth YC for a rectangular channel is Q square G to the power of 1 by 3. How you obtain this expression, I am not going into the derivation, but what is the general condition for critical flow? It is Q for critical flow, Froude number is equal to 1, or we can say that the square of the Froude number is also equal to 1, because Froude number is equal to 1. Therefore Q square T by Ga cube, from this we can get this Q square T by Ga cube equal to 1. Okay, where the characteristic line scale of the problem is A by T, where T is the top width of the channel. Okay, so this is the general expression which is valid for any type of channel. So if you use this expression for a rectangular channel, you will be getting that YC is equal to Q square by G 1 by 3. So Q square 7.64 by 9.14 whole square by G 9.81 raised to the power of 1 by 3. So the answer is 0.415 meter or 415 millimeter. Now the flow is tranquil. Now why the flow is tranquil? See, this is 400 mm is the critical depth, and what is the flow depth? Flow depth is 0.914 meter. Now since YC is less than Y, okay, since the depth of flow is greater than the critical depth, we say that the flow is tranquil. So if the depth of flow is greater than the critical depth, Y greater than YC, okay, means what? Y greater than YC means, see, Froude number equal to 1 is critical flow. Subcritical when Froude number is less than 1, okay, and supercritical is Froude number greater than 1. So this is one case, okay. And how you can say that the flow is subcritical or supercritical or critical based on the flow depth? It is critical when Y is equal to YC. It is subcritical when Y is greater than YC. So this is subcritical flow, so tranquil, okay. And if in and if suppose YC is greater than Y, if the flow depth is less than the critical depth, then it is rapid, okay. So I hope these problems are clear to you. In case of any doubt, you can ask now. In the next week session, we'll solve some more problem related to open channel flow and specifically hydraulic jump, which is a very important topic. And please practice some more problems like this that we have practiced today. So do you have any doubt? Okay, if not, then we can stop here, I think. Thank you. Let's again meet in the next class.